Okay, so this video is just going to be going over a couple of optimizations, really just small bits of code, and then we're going to talk a bit about the algorithm I plan to use. That should be all probably for this episode. I don't want to make this one too long, the last couple of videos have been really long, so just a couple of small tweaks I've made. Dimensions of board, I've changed to these dimensions because basically I wanted the X dimension, like the X width of the board and the Y width of the board, to be the same. I realised that with the old one, on the 14 by 14 size boards, it was having trouble picking up like the circles. Sometimes it was like, for this purple one down here, it was sort of like picking up this pixel like up in the corner somewhere up here, and not actually getting it. So I realised we needed to be a little bit more accurate with where the board was, so I've changed the dimensions of the board to this. I've also changed this thing right here, the size of square. This was the main issue, so I've changed this. Instead of size of square 430 divided by size of board, I've changed it to size of square is the dimensions of the board element 2, which is 470. Remember 0 indexing, so 0, 1, 2. Minus dimensions of board 0, so minus 30, because this is the X, this is the Y, this is the X, this is the Y. So I wanted X2 minus X1, so that's what I've got there. And then divide that by the size of the board. So size of board is obviously the number we return from this. This is just an int, so for this it'd be 14. So yeah, basically just trying to get these numbers a little bit more accurate, and now I've showed you that I can delete these comments. So that's one of the things I've done. I'm tempted to delete this locate colors, but I think we're just going to leave it there for now. It might be useful in future. But one idea for optimization I have, I'm not going to be doing this until the program's actually done and working. But if you look at the 5x5 and we run, you can see like it doesn't take too long to do. It solves it pretty much like probably under a second or so, maybe a little bit longer. But as we scale up and go to like the 14 by 14, to scan this board and detect every square, it takes quite a while. So you can see it's still running now, but it does work. So here's the grid, and I'm not going to go through all of this, but if we just look in this bottom right corner, because this was pretty much the problem area before. We've got grey, which is A. We've got S for whatever this colour is. M maroon. We've got Z for the purple. B for blue. M for maroon again. You can see we've got all these colours with the right gaps. We're not missing like the two dark blues up here. We're not missing. So yeah, I'm pretty happy with the fact that it works. It detects the size of the board properly. It fills in the colours properly. Obviously you can see this huge array of positions for all the centre of the squares. So yeah, pretty happy with that. The only thing is the speed, how I want to speed this up. I think the main issue for speed is the fact that we're detecting pixels on the screen. So we're using the PyAutoGUI.pixel method down here. I think we use this a couple of times, so we use it there. We also use it here. It's probably not needed here because we've already detected it up here. We could save this to some thing. Yeah, but basically what I'm thinking is that PyAutoGUI.pixel is quite slow. I'm thinking if the saved image we've got, which is a NumPy array, if we just scan that to see the values of the colours, that might be better. But I don't want to be messing about doing that right now. I'd rather just move on and get the logic down, get it solved, and get it drawn out boards, and then we can go back and optimize it later. So yeah, that's about it for the optimizations. And now I'm going to move on to what we're going to be doing next. So next we're going to be creating a new function. What this function is going to do is it's going to take the board of colours, so this huge array, and it's going to look for forced moves. So basically on the 5x5 over here you can see yellow can only go here, can only go here, and can only go here. And then you can see orange can only go here, here, and now only here. And now once orange is in there, and we know blue has to go up here because this is forced to go up here, then forced to go here. We know yellow has to go there. We know red can go around there. We know green has to go here. Red has to go there. Green has to go there. Now blue has to go there. So you can see like these are all forced moves. There's no no sort of moving 2 moves ahead and thinking like what's going to happen next and stuff. So our initial algorithm, what I want to do is I want to try and have like a function that is going to attempt to solve the board, but the way it'll solve the board is it'll just call loads of different functions that will all try their own method, and one of them should output something. So for example, the first one it's going to call is the one we're going to program. We're only going to program this one initially because it's only this one that's needed for like the majority of these boards. Like you can see, most of these can be solved using just forced moves. So you can see here, like even this one can be solved using forced moves. Pretty much all the 5x5s can, as far as I'm aware. I think probably all the 6x6s, and I know like even up to like 7x7 you get a lot of these that can be solved using forced moves. So you can see here, this is something that we're going to have to bear in mind in the actual solving. So this is forced to go out here, but now this is also forced out here, but when I click it and drag it out, obviously you can only move one side of it at a time. So what we're going to do, we're going to print out a solution board, then we're going to have another function that goes through the board and draws it as the game would like. So yeah, the program's going to actually solve it by drawing this out and drawing this out, but it won't actually draw it. It'll just be like on the matrix that it's like hypothetically drawn or whatever. So yeah, that's the plan in the next one. What else? So yeah, we're gonna use the forced moves function, and then get the program finished. And at the end, once it's actually done, we can then go back and update the function that will solve the board and like add in other heuristics and stuff. So I'm not too sure. I've had a think. I'm not too sure what else we can add, but there's probably things like so for example, I can't think of the exact situation on this board, but say we had the yellow's solution like had went something like this. We now know that this is wrong because of the fact that like this square is now isolated and the only thing that could go in it is yellow, and now yellow's not solved. So like there's a lot of little things we could probably add to it to try and help. And in the end we might just end up with like if there's no move being made for a while, just pick a random move and go for it. But yeah, I'm not too sure. I'm gonna have a think about that. If you've got any suggestions, feel free to let me know. And for now, this will be all. So in the next video, that's what we're gonna go through, and I will see you then.